Hello everyone! Today we are going to talk about the network layer and our IP address. Now within this, the network layer doesn't just include our IP address, it actually contains many protocols. For example, within this we have IP, ICMP, including IPS, but actually the most important are HMP and IP. The network layer is often referred to as the IP layer. As we mentioned before, our IP layer actually contains many things. So, what about IP? It is actually an abbreviation for Internet Protocol. When we talk about IP addresses in the future, it will actually be divided into two versions. They are IPv4 and IPv6 addresses. In our network, it actually provides a logical address for the devices on our network layer, which means it's a virtual address. And it is responsible for handling and forwarding these data packets. Now, let's take a look. Previously, we mentioned that if the application layer generates some data, what happens to this data now? After the data is generated, it will be transmitted to the transport layer. Once it reaches the transport layer, the data will be encapsulated, and this is what we call a data segment. Here, it doesn't matter whether it's a segment, a packet, or a bit. In our network, these all represent data and are just different names for it. Now, at the transport layer, for example, we add a TCP. It has a TCP header, and for the underlying network layer, this is all considered data. It will add the IP header that we learned about today. With the transport layer header added, and then the IP header, this becomes data for the second layer. When it reaches the second layer, it will add a frame header and a frame trailer. We will discuss this encapsulation format further later on. Today, our main focus is on a network layer, after being transmitted and encapsulated layer by layer, we finally reach the physical layer. At the physical layer, it is compiled into a bit stream and then transmitted through a network cable or a public line. Now, let's take a look at what is encapsulated in the IP header. Here, we will examine the IP header. Here, we can see a fixed header, which is 24 bytes. In this process, let's take a look at how many lines there are. 1, 2, 3, 4, and 5, a total of 5 lines. Each line actually ranges from 0 to 31 bits. 0 to 31 bits. This bit is small. 0 to 31 is actually 32 bits. So, what is the conversion unit between this and our 20 bytes? We need to know that 8 small bits equal 1 big byte. In this process, when we look at it in the future, you need to know that actually one line here equals 4 bytes. There are a total of 5 lines, which means 4 times 5 equals 20. This is a fixed number of bytes, meaning it is something that must be present. In this process, we can take a look at what is inside. The first thing is its version, which indicates which version you are using, either IPv4 or IPv6. Next is the header of our entire packet, because our IP header is variable. It includes optional fields and padding. We need to specify its length. If the IP header is 20 bytes, it doesn't need a specific field to indicate that it is 24 bytes because it is variable. Therefore, it needs to tell you, oh here, how long is this header in total, right? How long is the IP header in total? Now in this context, we must not say what this number will be in the future when compiling again. For example, a computer can only understand 0101. During compilation, originally, my IP header would have ended here. I say it hasn't ended yet, but because you haven't specified it, it doesn't know where the header ends and where the actual data begins. So in this context, I need to indicate besides these, what comes next. Next in this process is a type of service. You don't need to pay too much attention to this because it will be used in a later course content called QS. This is an advanced knowledge point for the future. Besides these, let's look here at a total length, which refers to our IP header plus the length of the upper layer data, which is actually here, because for me, in our network, we always say that these actually belong to our data. So in this context, well, the total length in this process we say is the total length of our entire IP header plus this data. So here, let's look further down. If I have something here, well, what is it? There is something called an ID value, right? ID we say in this process is called an identifier. This is actually something we will talk about later, used for the transmission of data. In this process, it is used for data identification during transmissions. So why do we need to identify it? Well, actually, there is a concept here. In the transmission process of our data, if the data is too large, it cannot be transmitted. The maximum is 1500 bytes. You cannot exceed this. You cannot say, oh, it's larger than 1500 bytes. Here, we mentioned the concept of fragmentation earlier, so we can divide a data packet into multiple fragments. Here is one of our routers, and here is another router, and here is another router, and here is another router. These 4 routers are connected together with network cables, for example. Once connected, we can see that our data is definitely transmitted through these links. In this context, each piece of data and each interface can transmit a maximum of 1500 bytes. It cannot exceed 1500 bytes. For example, if the upper layer generates a piece of data, how much is it? It is 6,000 bytes. Can 6,000 bytes be transmitted? No, it cannot. Why? Because each link can only transmit a maximum of 1500 bytes. So what do? We need to fragment it. We need to divide it into four parts. Now, why do we need to divide it into 4 parts? Just imagine when you are taking an elevator. For example, if an elevator can originally hold a maximum of 13 people, and then a 14th person gets on, it might become overloaded and it will trigger an alarm beeping continuously. Similarly, with MTU, it's like a bridge, where we say it can hold a maximum of 1500 people at once. If 6,000 people try to cross at the same time, they would have to go in batches. Otherwise, the bridge might collapse. On the link, there is a default MTU value of 1500. If the data from the upper layer is too large, I can't send it all at once over the link. So in this case, I need to slice the data, For example, here we have device 1, device 2, device 3, and our device 4. Now, in this scenario, let's say I generate a piece of data from the upper layer and the data size is 6,000. Now, I want to send the first piece of data to you, but I want to send this to you. For instance, I have already fragmented it, and then another piece of data is generated above. Because when everyone is using the network, you can't just say, at the same time, I only ever use one software. Nowadays, everyone might be using multiple software applications. For example, I have now generated another piece of data. It is 10,000. At this time, I might be generating a lot of data simultaneously. Suppose the data above is divided into 4 parts. The first part is 1500, the second part is also 1500, the third part is 1500, and the fourth part is also 1500. I have divided it into these 4 parts. Now in this process, logically, I should be transmitting them one by one to the right. If the 10,000 below also needs to be divided into parts, because it is divided into one part of 1500 and then into the second part. 1,500 might be divided into many segments in both BFWAM, and I have to segment a lot of data. Each one is different data, and each piece of data is different from the others. Once the data is segmented and sent to the other end, how does the receiver know which data was sent by the first device and which data was sent by the second device? This is a problem. Secondly, during this process, suppose I receive another piece of data. And another piece of data is generated. For example, it's 1450, which doesn't need to be segmented. How do I know it's the third piece of data? So here I need to distinguish it. At this point, a reception identifier will appear, meaning we assign it an ID. You need to say that for the first set of data, I assign the ID as 1. For this set of data, I assign it as 2. And for this one, we say it's 3. Right? So during this process, we understand, over here, they're all 111, meaning they're all from the first group. And over here, they're all 222, meaning they're all from the second group. I then know, you all belong to one group. So here, our ID number solves the problem of identifying the data we receive. Next, in this process, let's look at it again. If now these 4 are all 1s, right? These 4 are all 1s. Then how do I distinguish them? Hey, how do I know how many more fragments you have? I received 1 fragment, it's a 1. I received the second fragment, it's still a 1. I received the third fragment, it's still a 1. So how do I know when you finish sending the data? Therefore, there's another identifier here called MF, which indicates whether there are more fragments to follow. This is placed in our message, and I'll show you later. It's like a flag. If there are more, then this flag is set to 1, just like a switch. 1 means I've activated this function, and there are more fragments to follow. If it's 0, it means there are no more to come, right? No more. We say more fragments. 0 means this, within this, I have no more. Now, here I know whether there are more to follow, right? So I'm not the last piece. This is our flag. Now, after having these, you might say, I've received many fragments. I have them in hand, but how do I piece these fragments together? Let's take the example of the 6,000 above. If during this process, I have 4 pieces, right? 1 piece, 2 pieces, 3 pieces, 4 pieces, how do I know? Hey, is the transmission order correct? For example, if I receive the second one, first, can I sort them as 2134? That would definitely cause data chaos. So, what do? Therefore, in this case, we add something called an offset. Didn't we say to split this data into 4 parts? So, let's say during this process, we have them here as 0, up to 5999, which is a total of 6,000 bytes. Now here we can divide the first segment from 0 to 1499, which is exactly 1500. The second one is from 1500 to, let's see, up to 2999, which is also 3000. Then the third segment is from 3000 down to 4499, and the fourth one is from 4500 up to 5999. Now, when I go to label each segment here, let's take an example. Suppose for the first segment, what should I write? For the first segment, I would write 0. For the second segment, what should I write? For the second segment, I would write 1500. For the third segment, I would write 3000. For the fourth segment, I would write 4500. This way, I know exactly which position it is during future transmissions, allowing me to correctly identify it. Fill it in. So now, for example, if I receive a piece of data, if I receive a 0, I know it's the beginning. If I receive 3000, I know there's a significant gap in the middle, so I will fill it in the middle. Give it a shake, or in this case, I won't immediately place this 3000 into my entire sequence. I'll wait until I reach 1500, then I'll place the 3000 and finally 4500. This way my entire sequence is complete. So, during this process when the fragment lights up, it tells you where this fragment originally should be positioned. In this context, these parameters are very important. When placed in our diagram, first, this IE is what we mentioned earlier, for example, an identifier. This is a set of data. And if within this context it's all a set of data, it means the ID number is the same. The flex, which we mentioned as MF earlier, indicates whether there are more fragments to follow. This is one of the flag bits within it, meaning that. If I have enabled this function, and if I haven't, I set it aside. In the future, if this data doesn't need to be fragmented or cannot be fragmented, what should be done? Well, there's another flag bit called DF. If DF, meaning do not fragment, is set to 1. Then, in this context, it means that even if this data packet arrives and is larger than the range I want to transmit. Sorry, I can't transmit it either, right? I can't allocate it either, so at this point, it can only be discarded. In this context, it means that some data is actually not allowed to be fragmented, so I need to use this flag bit to indicate it. If it's 1, it means it cannot be fragmented. If it's a 0, it can be fragmented. Now, besides this, we also have our fragments, which means identifying where our data will be located in the network during transmission. So, the next technology we will discuss is called TTL, which stands for time to live. It refers to how many layer 3 devices our data packet passes through. In the future, we will learn about a device called a router. Each time a data packet passes through a router, which is a layer 3 device, the TTL will be decreased by 1. This acts as a preventive measure. Now, once a data packet passes through, the TTL value is reduced by 1. If the TTL value reaches 0, the data will be discarded. So why implement such a measure? For example, let's take a look here. If we say this is a device, and then this is a device, these 4 devices are connected together. It connects to this one. We say it then connects to this one. It connects to this one. And it connects to this one. Now, suppose I have connected one to this router here. Computer. And this computer wants to access some data in the future. But now, in this process of accessing data, I need to go through the router, which helps me forward it. Now here, my data comes from a remote location, and it wants to find some data. For example, this data is 1.1.1.1. Then the router checks its own table. The router checks its table to see where I need to go to reach the destination and where I need to send it. It checks and says it needs to be sent to this device. Then this device will check its own routing table and determine where to go to reach 1.1.1.1. After checking, it sends it to the device below, which then checks its own routing table. After checking, it sends it to the device on the left. The left device checks and then sends it to the device above. In many cases, this process is quite common. When our network administrators or network engineers configure this device, they might configure the routing incorrectly, causing the device to think it needs to take a certain path to reach the destination. In this case, what happens is it forms a loop. That is to say, if I don't recognize it, I pass it to you, and if he doesn't recognize it, he passes it to another, and so on. This means the data keeps circulating within our network and can never reach its destination. So, when can we say it will stop? It will only stop when the data communication from one device to another is received by a device that realizes, oh, this data was originally sent to me. He just stopped at that. But when all the devices receive it, do they know this data is meant for me? No, I'm just helping to forward it. So none of the devices here think this thing is meant for me. Hey, I'm just helping to forward it myself, and I don't have this thing. Oh, so this is called a loop. So is there a mechanism to avoid this situation? Because if it keeps looping, it will seriously affect our network resources. So our entire IP protocol has established a technology called TTL, time to live, to prevent loops. Based on TTL, several values are set, and different systems have different values. For example, some devices might have a value of 255, some devices might have 128, and others might have 64. As for different manufacturers and models, there may be differences. Let's take 255 as an example in this process. When the data is initially generated, it will be 255. Each time it passes through a device, it decreases by 1. So here we say that passing through this device will decrease it by 1, making it 254 there. Passing through another device will decrease it by 1 again, making it 253 here, and it will keep decreasing continuously. There will always be a moment when we keep decreasing it. Eventually, it will reach a certain device. For example, after many cycles, it reaches here, and 2 becomes 1. Once it sends out a 1 here, and it reaches this device, it says that after receiving it, I will locally decrease it by 1 more. If the resulting value is 0, then I will discard this packet. After discarding it, I don't just silently drop it. I will inform the original sender, telling them that this data, well, didn't arrive, right? I will return a value to them, informing them that the TTL has expired. This is all based on what we might learn later, which is encapsulated using an ICMP message. In other words, when there is a loop in our network, we can use this TTL to prevent it. This function is called loop prevention. Besides TTL, there is also the concept of protocols in our network. What is a protocol? In my network, during transmission, since all data is represented in 0101, I need to identify, hey, in the future at the network layer, once I receive it, if I want to pass it upwards. For example, when I decapsulate, I receive some data, and first I will remove the second layer's encapsulation header and trailer, and then remove the third layer. After removing the IT header, I then transmit it upwards to the transport layer for parsing, where I need to know what kind of protocol I should use to handle it, determining which protocol to use to further process this packet. So here, you also inform it, what kind of protocol the upper layer originally used. If you see a 6 here, it means it's our TCP. If it's 17, it's our UDP. If it's 1, it's our ICMP. Based on this, I can identify what kind of protocol my upper layer protocol is, making it easier for the other party's application to decapsulate. Besides this, we also have our header checksum. What does the header checksum mean? It refers to a check performed on the IP header to see if any issues occurred during transmission. If there is a problem, then there's no need to receive it. The most important parts are definitely our source IP address and destination IP address, which we will gradually explain to everyone in more detail later on. If anyone wants to learn Huawei certification technology, message me. More info in the comments.